Welcome to Empowered Learning. This video is a continuation of the video on limit laws and learning how to evaluate the limit of a function algebraically. So what I want to do in this video is look at some more limits of functions to where we have to do some more algebraic manipulation to them to be able to figure out what the limit actually is. I also want to take some time to look at some limits where we are going to have to use a method called utilizing the conjugate radical. And so you'll see how using this conjugate radical technique will allow us to be able to rewrite the limit of some function, or I should say rewrite the function in such a way to where we can actually evaluate the limit, because if we don't do that, then the limit will be in what we call an indeterminate form. And an indeterminate form is just a form of a limit to where if you get that outcome, it really doesn't tell you anything significant about what the limit of that function is. And so it calls for us to have to rewrite the function in a way so that we can actually see what's going on with the behavior of it. So we'll go ahead and do this first example here. And I'm actually going to do this first example in two different ways. And so the first way that I'm going to do it is more of a conceptual type of way. The second way I'll do it will be more algebraic and computational intensive. And it's more the traditional way that's taught in a first year calculus course. So the first thing that I want to look at here is when we say the limit as x approaches infinity of this particular function here, notice that this is a formal way of asking about a certain property of this graph. Okay. Now, in other videos that I have, I'll talk about how to evaluate the limit of a function and interpret what that means as far as the property of the graph that limit is trying to highlight. And through this video, I'm going to make that point. But in that particular video, which will be called Summary of Limits in Their Interpretations, I actually kind of go through everything all at once so that when you see a limit, not only are you thinking, well, hey, how do I computationally figure this out? But you'll also be able to know in the language of calculus what that limit is actually trying to ask you about that function. Okay. Now, if we look over here, we see that we have this property that's very important here. Okay. And this is actually a theorem, but I've just kind of shortened it. All this is really saying is that whenever we have functions that are of the ilk 1 divided by x raised to the r, and of course functions like that you know of are 1 over x, 1 over x squared. These are some of the more popular ones, where 1 over x basically looks like this. And you have a vertical asymptote here at x equals 0, horizontal asymptote at y equals 0. 1 over x squared, very similar, but it looks like this, where again you have horizontal asymptote at y equals 0 and vertical asymptote here at x equals 0. So notice here that for both of these functions, as my x values get larger and larger, my y values tend to go toward the x-axis, which means that my y values are getting closer and closer to 0. So that happens as x approaches positive infinity, also happens as x approaches negative infinity. And it happens that way for this function, whether we have 1 over x, or in general, I should say 1 over x raised to some odd integer or rational number. We could say it that way. And here also, if we have an even integer or rational number, or really I should say even natural number. Okay. So the point that I want to get here is that we know that this is true for these types of functions here. And so what we want to do is utilize this in actually evaluating the limit of this particular function here, okay? And we're going to use this whenever we go through the more computational way of evaluating this limit. Now, what I want to concentrate on first is to take more of a conceptual approach, and I'm going to leverage what we learned back in pre-calculus algebra to be specific. Some of you may know that as college algebra. We're going to leverage some of that knowledge to be able to figure out what this limit is relatively quickly. And so I'm going to erase all of this, and then we'll talk about how to approach this limit from that perspective. So if we evaluate the limit of this particular function here, the first thing that we want to note is from our limit laws, we know that since we have a limit of square root of some rational function, and it really doesn't matter what the function is here, our limit laws tell us that we can take this limit operator and we can slide it under the radical here, okay? So our very first step would be square root of, and then we'll say limit as x approaches infinity of, and then we'll just write out this rational function here. And I'm going to fix that. Yeah, so this should be a 2. All right, so this is our first step here, okay? Now, if we take what this limit is actually trying to communicate to us, remember that limit means behavior. So what I want to know is, how does this particular rational function behave as x approaches positive infinity? If we think about that for a second, what we're really asking here, since x approaches positive infinity is toward the end of that graph on the right side, what we're really asking for is the end behavior of this particular function, okay? So whenever we evaluate the limit of this rational function as x approaches infinity, it's just another way of saying, well, hey, what is the end behavior of the function? Now, if you remember from pre-cal, one of the things that we studied is the concept of a horizontal asymptote, okay? And a horizontal asymptote is essentially the end behavior of a function whereas x approaches either positive infinity or negative infinity, depending upon what direction you're looking at, the y values tend to go toward, but not necessarily actually get to a certain specific y value, okay? Now, from pre-cal, we know that since the degree of the numerator, which is 3 here, matches the degree of the denominator, which is 3 here, how we could figure out what the horizontal asymptote is that we just take the quotient of the leading coefficients, okay? And for the numerator, the leading coefficient is 12. And for the denominator, the leading coefficient is 3. So we can see here for this rational function here, we have a horizontal asymptote at 4, okay? Now, what this also tells us is that as x approaches infinity, this means that this polynomial in the numerator is going to act more like its leading term than all this other stuff. And the same thing happens in the denominator, okay? So because of that, we can say that square root of the behavior of this rational function will be just like square root of the behavior of this rational function, okay? And notice here that on the inside of our limit, all of what we see here, that's just going to simplify to 4. So here this would just be limit as x approaches infinity of 4. And of course, the limit of any constant is just that constant. And of course, square root of 4 is just 2. And so this is the quick fast, conceptual, and dirty way of evaluating this limit. Okay. And we do that by sort of cheating and using some of the things that were taught to us in pre-cal to be able to do that. And depending upon what course you're taking and what professor says, hey, you should do it this way or do it that way, this may or may not be acceptable. So that's one of the reasons why I'm actually going to work this problem another way, so that depending upon which way is acceptable, you know how to do both. Okay. And just know that the next example I'm going to do, like this one, will be the more traditional way of actually evaluating the limit. And it's what you're going to see in most textbooks whenever you learn about this particular topic or learn how to solve these kinds of problems. So we're going to go ahead and do that next. Okay, so we're now going to evaluate the same limit, but we're going to do it from a more computational, traditional aspect. Now, to start off, it's pretty much going to be the same. We can take our limit operator and slide it under the radical here. So we're still going to have square root of limit as x approaches infinity of all this business here. Okay, so all that's still going to be the same. Okay, now instead of me writing this out right now and having to keep on copying that step, what I'm going to do is I'm going to actually work on this particular function here to get it into a form that I want, so that once I get it into the form that I really need, then I'm just going to stick that equivalent way of rewriting this function into the limit, so that I don't have to, do those steps and keep on writing square root and limit as x approaches infinity so many times. Okay, so let me go ahead and write this out. And then we're going to concentrate on getting that other function, that rational function, to look the way that we want it to look. Okay. So here I'm going to say note. And now we're going to work on rewriting this particular rational function in the way that we need it to look, so that when we do this next step here, we're going to replace all of this with what we actually need. And we're going to use this fact here to be able to evaluate the limit. So what we want to do with this function here is we want to rewrite it in such a way to where each one of these terms here will actually look like some number divided by x raised to a number. Okay. Now, the best way that we could probably do that is we could take this particular function and multiply it by 1, but we're going to make 1 look like 1 over x cubed divided by 1 over x cubed. Okay. And so when we do this, this will create the 1 or some number divided by x raised to a number that we need, so that we can use this property here whenever we actually slap back on this limit operator here. Okay. Now, the reason why we are using 1 over x cubed divided by 1 over x cubed versus, let's say, 1 over x squared is that we want to use the exponent that is the highest one, that matches the degree of the highest degree of any polynomial that's in our rational function here. So for instance, if I had let's say 12x cubed here, but I had 3x to the 4th here, then I would want to take this and say 1 divided by x raised to the 4 divided by 1x raised to the 4. Okay. If I had 12x raised to the 4 here, and this was still 3x raised to the 3, I would still want to try to do the 1 divided by x raised to the 4 for both numerator and denominator here. Okay. And usually when it works out great, like how it will in this example, we will end up getting some real number for the limit. Other times when it does not work out as great, we end up getting something like 1 or some number divided by 0. And that basically just tells us that we have an oblique asymptote, meaning an asymptote that is slanted, or it may be parabolic, but it's just not a horizontal asymptote. Okay. All right. So if we work this out here, I'll take this 1 divided by x cubed, and I'm going to distribute it to all 3 terms. If I do that for the first term, then 12 divided by x cubed times 1 over x cubed is just going to give me 12. Okay. If I do the same thing, negative 5x times 1 over x cubed, that's going to be negative 5 divided by x squared. And then, of course, the last term will just be 2 divided by x cubed. If we repeat this process in the denominator, I'll have 1 over x cubed plus 4 over x plus 3. And so this is the form that we need to be able to have our function in, so that when I go and write this next step here, and I replace all of this with what I have here, notice that now I can use my limit laws. And my limit laws are going to say that, hey, if I'm taking the limit of the quotient of 2 functions, then that means I can take the limit of each function in the numerator and denominator. Okay. And then, of course, my limit laws will also tell me that if I'm doing the sum or difference of functions and I want to find the limit of that, I can just take the limit of each term separately. Okay. So I'm saying all this because I'm going to skip some steps here just to kind of save time and space. So therefore, we're going to say, and I'm just going to come down here. And now we're going to say that this is going to be, and I'm going to rewrite it like this now. Okay. And so now at this point, technically, what I should do here is I should go ahead and rewrite this as square root of limit of numerator divided by limit of denominator. And then the next step should be, I'm going to write limit for 12, then limit of 5 divided by x squared, limit of 2 divided by x cubed. But since we kind of already know about the limit laws, we're going to skip that step. And what we're going to do now is just apply the limit to all of these. And so essentially what I'm going to do here is everywhere where I see an x, I'm going to now replace it with infinity. Now, if we were just working with, regular function, did not have this whole limit operator in this problem here, what I'm doing here would be technically incorrect. But because of the fact that I'm actually trying to evaluate a limit, I can actually do this. Now, we know from this fact here that as long as the limit of something divided by x raised to a number is, if x is going to infinity or negative infinity, the result is going to be 0. So that means all of these terms here, this term is 0, this term is 0, this term is 0, and this term is 0. And so once all that's done, all I have left in the numerator is 12, and all I have left in the denominator is 3. And of course, from that, you can see now we're back to where we were when we did the very first example. And this is just square root of 4. And of course, square root of 4 is just 2. And so that is the more traditional approach to evaluating the limit of a function here, like this. Now, if you're working out these problems and you're saying, all right, well, great, I understand the whole concept here. How do I actually work out this problem in the way that I need to, but yet still have the right notation and have it be as efficient as possible? Okay. So if I were giving you a suggestion on how to do this problem, the first thing I would say is I would actually come and do this part first, meaning note, I would work on this portion first here. And then after you do that, then I would come here and I would write this step and then this step here and then this step down there. So the most efficient way to do it is to work on getting your function that you need to take the limit of in the proper form first so that you could use this fact and then use it. Okay. And so I just started off here with this example because that's kind of how I did the last example. And I wanted to make the connection in between the two. All right, so we're going to go ahead and move on to the next example. And in the next example I'm going to introduce you to what's called the conjugate radical technique for being able to evaluate some of the limits that you'll be faced with. So for our next example here, notice that we're being asked to find the limit of the difference of these two square root functions here. Okay. Now, I have a hint here, use conjugate radical technique, and I'm going to tell you what that is or show you what that is. But the first thing that I want to do is I want to make sure that you understand why we're actually using this technique. Okay. Now, if we did not know about this conjugate radical technique, the most that I could probably do here is really just plug in infinity. Okay. And so if I did that, if I had infinity here and infinity there, then I would just have square root of infinity squared plus infinity would just be infinity, minus same kind of thing here. And this would just be infinity minus infinity. Okay. Now, infinity minus infinity, contrary to popular belief, is not zero. Okay. You would think that, but the thing is that you can only say that something minus that same something is zero when you know exactly how much it is. Since we don't know how much infinity is, there's no way for us to know whether this infinity here is bigger or smaller than this infinity. Because remember, we're not talking about numbers here. We're talking about limits or the concept of behavior. Okay. So because of that, this is technically what we call an indeterminate form, because again, infinity is a concept, not a number. And I don't know if this infinity is bigger than that one or vice versa. Okay. So in this current form, it doesn't really tell me much about the behavior of this function. So what I'm forced to do is to find another way to be able to evaluate the limit of this function here. And essentially what that means is I'm going to have to rewrite what this function looks like legally from an algebraic standpoint to be able to really see what's going on with the behavior of it. Okay. Now, the conjugate radical technique just says, hey, I'm going to multiply this particular function by 1, but 1 is going to look like the conjugate of this particular function here, which is this divided by itself. Okay. And so I'm going to go ahead and write that so that you can see what that looks like. All right. So we're going to start off by just saying note. Let me here. Note square root of all this business here. This is going to be equal to the same as what I just wrote. And I'm going to put this over 1. But now we're going to multiply this times square root of ax plus square root of x squared bx. And I'm going to do the same thing in the denominator. Okay. So we have that. And now what you see here is that we need to multiply numerator and denominator here. Okay. Now, of course, the denominator, not much to it. Let me switch this color here. So not much to it. Denominator still just is going to be square root of x squared plus ax plus square root of x squared plus bx. However, our numerator, when we multiply that out, that's going to look a little different. Okay, and to make life easy for us, note here that if we think of this first term as a and the second term as b, then we have a minus b times a plus b. And of course, a minus b times a plus b is just going to be a squared minus b squared. Okay. And so if I take square root of x squared plus ax and I square it, I'm just going to have x squared plus ax. Okay. Minus, if I look at b, which is square root of x squared plus bx, and I square it, I'm just going to have, in parentheses, x squared plus bx. Okay. And so that simplifies the process for us a lot to be able to multiply this out. So now that we have that, then of course, I'll just distribute these two, this negative here, both terms here, and that ends up giving me x squared plus ax minus x squared minus bx. And all that over same thing I had in the denominator before. Okay. And of course here, the x squared minus x squared, all that's going to cancel to 0. And here I just have ax minus bx, and I'm going to rewrite it as a minus b and just factor out the x here. And then just write the denominator same way. So now at this point, we're feeling pretty good about ourselves because we've rewritten our function here in a different way. But if I was to take what I had here and I was to apply a limit as x approaches infinity, I would still have the same problem because, and I'm just going to go ahead and write it in here just to kind of make my point. So let's say right here, hypothetically speaking, and I'm going to erase this equal sign here just for a second. Let's say if I went ahead and said limit as x approaches infinity here, okay? If I did that, since a and b are just constants, the most I could do is just write infinity here for x. Everywhere where you see x, write infinity. And I would still end up having a situation like this where I would have infinity over infinity. Now, again, infinity over infinity is another type of indeterminate form whenever we talk about limits. And that is because I don't know if the infinity in the numerator is bigger or smaller than the infinity in the denominator. And since I can't determine that, since I don't know how much infinity actually is, then I'm kind of stuck at this point. Okay. Now, for those of you that are watching this particular video and you're already sort of familiar with some of the calculus concepts, in particular, you're familiar with a concept called the L'Hopital's rule, you could try to do that with this. However, that would constitute you having to take the derivative of the numerator and the denominator separately and evaluating the limit again. And kind of messy to do that with this, okay? And plus, if you're watching this video and you're kind of following along the series of videos that I have, we're not at that particular point yet, okay? So I'm going to approach in trying to rewrite this some more in a way to where once I'm done with it, algebraically speaking, it's going to be in a form that's going to be useful for me to be able to do the limit as x approaches infinity, and I will be able to evaluate what that limit's going to be without having to do any apply any concepts that are like way further ahead in the first year calculus course. Okay. All right, so let's go ahead and put this equal sign back in here. Now that we understand that we need to do a little bit more than what we've done. And let me get my color switch back to what it should be. All right, so we'll put the equal sign here. We'll get rid of all this business here. All right, so now what we need to do is find another way to be able to rewrite what we have here, okay? Now, the problem here is that I have infinity over infinity, okay? If I had, let's say, some number divided by infinity, that would be great because any number divided by infinity from a limit perspective is approaching zero. So it's not a problem for me to have infinity in the denominator and just have a number in the numerator. That would be fine. Also, let's say if I had infinity over some number, then of course that's just going to approach infinity, and that is okay too. Not an ideal case, but you know, if that's what the behavior of the function is, and that's what it is, okay? So we need to find a way for us to try to get rid of the occurrence of infinity happening either in the numerator and or denominator, okay? Now, the approach that I am going to take here will be the following. Since I just have an x here in the numerator, I want to try to get rid of that x, okay? And the way that I could do it is I could say, well, let me multiply the numerator here by 1 over x, okay? Well, if I did that, then of course I could do the same thing in the denominator, right? So I could come here, and I'm just going to write this in like this. I could say 1 over x like that as well, okay? Now, if I did that, that would be great because in the numerator, I would just have a minus b, which is exactly what I want. However, I have a problem in the denominator here because I technically can't multiply 1 over x. Well, I can try to multiply 1 over x by both of these terms, but the issue is that I need this 1 over x to be able to get on the inside of these radicals here, okay? So what I'm going to do instead is, instead of writing 1 over, just writing 1 over x, I'm going to rewrite it as square root of 1 over x squared. And of course, I'm able to do that because 1 over x is equal to 1 over x squared as long as x is greater than 0, okay? So this is the equivalent of that as long as x is positive. And since we're taking the limit here as x approaches infinity, I can assume that the x values that I would be plugging into this function to study its behavior would be positive, okay? So because of that, I'm going to come here and rewrite this as square root of 1 over x squared, okay? And so by doing that, now I can legally get that 1 over x squared multiplied times the terms inside of the denominator for both terms in the denominator, okay? All right, so I'll switch colors and then we will write out what the result is. So in the numerator here, when I do this, I'm just going to have a minus b. Simple enough. Okay. In the denominator, I'm going to have square root of x squared plus ax, all that divided by x squared, plus square root of x squared plus bx divided by x squared. Okay. And if I simplify that further, then I end up having a minus b all over 1 plus a over x plus, and I'll have 1 plus b over x. Okay, and of course that's so because x squared divided by x squared is 1, and x divided by x squared is just 1 over x. So that's how we get this first term here, and same sort of thing happens with that second term. And so now this is the form of that function that I originally had that I need to have it in so that I can effectively evaluate the limit of this particular function that I was given. Okay, so at this point, what we will say is, therefore, the limit as x approaches infinity of square root of x squared ax minus square root of x squared plus bx, this function will behave or act just like this one. Okay, so what we've just found. And so when we rewrite these limits, that is essentially what we're saying. The behavior of this function is just going to act like the behavior of this function. And so now at this point, again, we're at a point to where I can essentially just plug in infinity everywhere where I see x. And that is because from our limit laws, I can do limit of the numerator divided by limit of the denominator. Since the limit of a constant is just a constant, of course, the result will be a minus b on top. For the limit operators being in the denominator, I can do the limit of each term separately. And from my limit laws, each limit operator should be able to slide under the radical of each of these terms. And then, of course, I could evaluate the limit of 1 plus a over x and 1 plus b over x separately. So I'm going to skip all those steps, but I wanted to actually say it so that you know that technically if we were being very staunch on writing every single step, that's what it would be. So at this point, I'm just going to replace all x's with infinity. And of course, we know that this term is going to go to 0. That term is going to go to 0. And we essentially have just a over b divided by square root of 1 plus square root of 1. And we know that square root of 1 is just 1, so 1 plus 1 is 2. And this would be our final answer here, okay? And what this is communicating to us, so if we go back to the beginning here, what we wanted to know is what is the behavior of this particular function as x approaches infinity? Or put another way, what is the end behavior of this particular function here? And so we see that after going through this whole process, that what we end up getting is some real number here. So we know that the end behavior approaches some y value for that particular function. To put that in another way, we essentially have a horizontal asymptote at y equals a minus b divided by 2, okay? And since we don't know what a and b are explicitly, we can't say exactly where it is. So what we've done here is actually found what the behavior is for a family of functions, depending upon what A and B are. What the end behavior is for this family of functions. And as long as we know what A and B are, we can tell what the horizontal asymptote would be for that specific function. Okay. All right, so let's move on to the next example. So for this next example, we're trying to do somewhat the same thing in that we're basically trying to find out what is going to be the end behavior of the function that we're given. Notice that the function that we're given now is a rational function. And also notice that this rational function, the degree of its numerator is higher than the degree of its denominator. Okay, and I say that because we can look at this particular limit, and if we interpret it as saying, hey, what is the end behavior of this function here, we can actually look at this and tell what the answer is. Okay, just by using what we know from pre-calc. So now that we understand that this is just asking, hey, what is the end behavior of this particular rational function? Rational functions have end behavior of either being a horizontal asymptote, so that means it just smooths out along some horizontal line, either goes up to positive infinity or down to negative infinity. Those are only three choices you have. And since the degree of the numerator for this rational function is higher than the degree of the denominator, we know that it's going to be one of these two choices here, because we don't have a horizontal asymptote in this case. We end up having what's called an oblique asymptote. And in particular, this oblique asymptote will be a slant one, meaning that our asymptote is not horizontal. It will look like a line, either with a positive slope or a negative slope as x approaches infinity. And so we can easily figure out which one it's going to be just by taking this rational function and dividing the numerator by the denominator. Okay. Now, if we take the approach like how I did in the very, I think the example that I did, the very first one I did in this video, since this is a rational function, if I take that approach and sort of utilize what I know from pre-cal, I could say that the behavior of this function as x approaches infinity is going to act just like the behavior of this function. And of course, as x approaches infinity, this polynomial in the numerator is going to act more and more like x cubed, and this polynomial in the denominator is going to act more like minus 2x squared. Okay. And so if I simplify what's inside of my limit here, this is essentially just going to be x divided by negative 2, or 1/2 x. And if I take the limit of basically negative 1/2 x, then that's just going to be like infinity divided by negative 2, which goes to negative infinity. And so again, if we sort of take the cheat way to evaluate this limit, it ends up being negative infinity. Okay. So now what I want to do is I want to work this problem out again, but I want to do it in a more traditional way. And so here I wanted to show you the technique that we did at the very beginning of this video with the very first example. And I wanted to also clarify the strategy that we would use for this. Now, of course, one way for us to actually do this is just to divide this polynomial by that one, and we'll get like a negative 1/2 x, and then they'll have something else left, and we can approach it that way. I'm going to try to do it a little bit cleaner by just saying, let's multiply the numerator and denominator of this particular rational function by 1/x² divided by 1/x². Now, I'm going to explain why we want to do it by 1/x², 1/x² divided by 1/x² versus 1/x³, like what I was saying earlier, by going with the highest exponent here. So really what we're trying to do here is pick, do I want to get rid of the numerator or denominator here, okay? As far as having the infinity on the bottom. And the safest way to do this is by actually taking whatever the degree of the denominator expression is and doing the 1 over x raised to the whatever that number is divided by the same. And so by doing that, what that's going to do is keep the integrity of how this particular function will actually act, okay? So to make a long story short, if I was to say, well, let's multiply this by 1 over x cubed divided by 1 over x cubed and work that all out, I would still get that the limit doesn't exist, meaning that I would get an infinity, but I wouldn't get the negative part here. And the reason why I wouldn't get the negative part here is because once I do all this, my denominator would just be 0, okay? And of course, 0 minus 0 is just going to be 0. And so I would lose that negative portion there because of the fact that the degree of x cubed is larger than the degree of x squared. So it really doesn't matter what it is. But by me dividing by 1 over x squared divided by 1 over x squared, I keep the integrity of having that negative here that will give me the same thing I got in this case. So that's why we want to take that approach. All right, so let's go ahead and do that now. So if we're doing this the more traditional way, and I'll make some separation here. Let's say note. I'm going to say let f of x equal this particular function here. This will be 5 minus that. And we're going to multiply this by 1 over x squared over 1 over x squared. And this same is just multiplying this by 1. If we do that, I'll have x in the first term minus 2 over x plus 3 over x squared. And in the denominator, I will have 5 divided by x squared minus 2. And so if I wanted to take the limit as x approaches infinity of f of x, of course, that's the same as saying this. Then that's the same as saying taking the limit as x approaches infinity of all this business here. And of course, since we have the limit here as x approaches infinity, what I can essentially do is just plug in infinity everywhere where I see x, and then use that fact that any number divided by infinity or infinity raised to a power is going to end up being 0. So have the situation here, infinity minus 2 over infinity plus 3 over infinity squared. 5 over infinity squared minus 2. This goes to 0, that goes to 0, that goes to 0. And you see how we still end up with the infinity over negative 2, which goes to negative infinity. All right, now in terms of what all of this actually means, again, what we're saying here is that the end behavior, because limit means behavior, the end behavior of this rational function is going down like this as x approaches as x approaches positive infinity, okay? So we know that if we were looking at the graph of some rational function and not really concerned about what the rest of it looks like, but if I had the graph of some rational function and I wanted to know as x went on to infinity, what is this particular graph going to act like? Well, I just know that it's going to go down like this, okay? Now from pre-cal, we understand that the way it's actually going to go down is going to go down linearly like the line negative 1/2 x. So you would actually have like a, didn't quite draw that right. But basically, you are going to have a line that has a negative slope that goes through the origin as the asymptote, and as x approaches infinity, this graph would get closer and closer and closer to this particular line here. And we would have to decide if the function was like up here and eventually would go down like that, or if it's somewhere down here and eventually curves and does like that. That's something that we don't know right now. We could figure it out, but that's not really the scope of the example, so we're not going to worry about it. All right, so just to recap here, we know that from using what we know from pre-calculus or college algebra, the limit above is suggesting that our rational function being evaluated for its behavior has an oblique asymptote. We can put slant here because the difference in degree of numerator and denominator is just 1. Okay. And of course, we said that the oblique asymptote is actually going to act like 1/2 times x. So it's going to act like this. And again, the way that I got it is essentially just by evaluating the limit this way and knowing that as x approaches infinity, this particular rational function will act more like the quotient of its leading coefficients. We could also do it the traditional way and just divide this cubic function divided by this quadratic one, and we'll see that the quotient ends up being -1/2 x as well. Okay. All right, so let's move on to the next example. So another thing that we do in the first year calculus course is we take the concept of a vertical asymptote and horizontal asymptote and explain, well, hey, how do we formally say we have this sort of thing in terms of limits? And so in this example, we want to take this rational function that we have, and we want to be able to show or determine, in this case, that we have vertical and horizontal asymptotes in the function. Okay. Now, to do this, you kind of have to know what you're looking for. Okay. And so we know that for vertical asymptotes, we need to figure out the values of x for where the denominator goes to 0. Okay. And so if we're looking at this, so 2x squared plus x minus 1, if I factor the denominator here, that's just going to factor to x minus 5 times x plus 4. Okay. So from what we know from pre-cal, we know we have vertical asymptotes at x equals 5 and at -4. Okay. In the language of calculus, calculus doesn't understand this. Okay. So we're using like baby talk to really say that, hey, we have a vertical asymptote here. For calculus, what we have to do is we have to say the limit as x approaches 5 of f of x, and we have to expect to get either a positive or a negative infinity here. Okay. And the same thing should happen whenever we do the limit as x approaches -4 of this function. We should either get a positive or a negative infinity. Okay. And so by us evaluating the limit of this particular rational function and getting either positive or negative infinity when x is approaching a specific real number, we know at that point in the language of calculus that we have a vertical asymptote. Okay. Now, again, this is just a formality thing because, again, depending upon what first year calculus course you're taking and how your instructor is, they may only accept you to be able to express that you have a vertical asymptote in terms of limits. They may allow you to be able to do this whole pre-cal thing and just kind of skip that. I'm just here to show you, if you have to do it in a more formal sense, how that actually needs to look. All right, so we're going to show that this particular function here has vertical asymptotes at x equals 5 and x equals -4 by using limits. So I'm going to erase all this, and then we're going to show how we can actually do that. Okay, so let's go ahead and first verify that we actually have a vertical asymptote at x equals -4. Okay. So first thing we want to do is do note again. We're going to say f of x can be rewritten, well, can be written this way, but then we're going to rewrite it. And here I'm going to divide both numerator and denominator by 1 over x squared. So we do that, then we'll have 2 plus 1 over x minus 1 over x squared, and 1 minus 1 over x minus 20 over x squared. Okay. And we're going to use this expression here to be able to evaluate our limit at -4 as x approaches -4 and at 5. Now, part of the reason why we want to do this formally is that all we've actually done here when we said that we have potentially a vertical asymptote at x equals -4 and 5 here is, notice that all we did was find the zeros of the denominator. Okay, we haven't done anything with the numerator. And so my point here is that even though this is not going to be true in this case, from the language of calculus perspective, since we have not factored out what the numerator is, we don't know whether this is actually going to be something like 2 divided by 0, or if it's going to be 0 divided by 0, okay, as far as the limit is concerned. If we have something like number divided by 0 is concerned, as far as the limit is concerned, that's great, because then that just goes to infinity, okay? But if we have a 0 divided by 0 case, this is another indeterminate form. And again, from a limit perspective, I can't say whether this function in the numerator decreased to 0 faster than this function did, okay? And so because of that, as far as the behavior of the function, that doesn't really tell me much, okay? And so this is the main reason why, for those staunch calculus people who like to say, well, no, you need to do show vertical and vertical asymptotes in terms of limits. That's why they do it this way, okay? All right, so now that we have this, then let's go ahead and say limit as x approaches -4 of f of x is just going to be limit as x approaches -4 of all this business here. And again, I just wrote it as f of x here so I could skip having to write all this at the beginning. So I'm legally cheating. All right, and this will be 1 over 1 over x minus 20 over x squared. Now, at this point, for each, if we take the limit of the numerator and the limit of the denominator separately, and we apply the limit operator to each term can be looked at as a function, and each of these terms will, if I apply the limit to it, I'm not going to get something where I have a number divided by 0, okay? So because of that, I don't have to worry about taking the limit of each of these terms being something that may be undefined or does not exist, okay? So if I do that, then I'll say 2 plus 1 over 4 minus 1 over 4 squared, or -4, I should say. And that's going to be -4 squared here. And this will be 1 minus 1 over -4. And this will be minus 20 over -4 squared. All right, so if we go ahead and clean this up here, this is going to be 2 minus 1/4 minus 1/16 over 1 plus 1/4 minus 20 over 16. And just to make doing the math a little bit more simple, I'm going to multiply numerator and denominator by 16. So I'll have 32 minus 4 minus 1 all over 16. What's that? Plus 4 minus 20. In the numerator, I just have 32 minus 4, which is going to be 28, and 28 minus 1 is 27. In the denominator, 16 plus 4 is 20, 20 minus 20 is 0. And we see here, limit-wise, a number divided by 0, that approaches infinity. And so, because we have this output here that we took the limit of our function as x approaches a specific x value and we got an infinity as a result, this verifies for us that we actually have a vertical asymptote at x equals -4 for this function. Okay. All right. So if we did the same exact thing for this particular function when x is 5, I'm just going to rewrite over what I have here so we can see that we'll end up with something similar. So I'm going to erase this and we'll just write over it. So we have 5 here. And everywhere where I have a -4, I'm just going to replace it with the 5. And of course, we'll have different numbers here. So we'll figure out what all this is later. All right, so I've gone in and replaced all the -4s with 5s. And so now we're at this point here. So we have 2 plus 1/5 minus 1 over 25. And denominator would be 1 minus 1/5 minus 20 over 25. And again, to make the math easier, I'm just going to multiply by 1, but let 1 be 25 over 25. So now that I have 50 plus 5, because 25 times 1/5 is 5, minus 1. And then same thing in the denominator here. So it'll be 25 minus 5 minus 20. And of course, in the numerator here, 50 plus 5 is 55, minus 1 is 54. And denominator, 25 minus 5 is 20, minus 20 is 0. And of course, that still goes to infinity. So we see that we also have a vertical asymptote here at x equals 5. So now for the horizontal asymptote for this, and this shouldn't have an S here because we're only going to have one asymptote here. So I'll just go ahead and scratch that out. So we're going to do the same thing. We'll use this same representation of our rational function, but we'll take the limit as x approaches infinity. So we'll say limit as x approaches infinity of our function f of x. And this will be the same as limit as x approaches infinity of all this business here. And of course, from here, we know from previous examples that all we have to do is replace everything everywhere where it says x with infinity. Of course, all these terms are going to 0. And all we have left is 2 divided by 1, which just ends up being 2. So this lets us know, or we verify that we have a horizontal asymptote on the horizontal line y equals 2. All right, so for our next example here, we're asked to find the limits as x approaches positive and negative infinity for the function x cubed times x plus 2 squared times x minus 1. And we want to use this information together with x, y intercepts to give a rough sketch of what the graph of this function should look like. Now, if you remember what I've been saying earlier, anytime we're asked to take the limit of a function as x approaches positive and or negative infinity, what we're really asking for is the end behavior of that function. So what I've really done is I've taken a problem that you would normally see in a college algebra or pre-calculus algebra course, and I've phrased it using calculus terminology. Okay, so if you solve this particular problem in a pre-cal course, it would just basically say use what you know about the x-intercepts, multiplicity of the zeros, and end behavior and degree of this polynomial to be able to draw a graph of it. Okay? And so the end behavior portion of it, we're just going to use limits to be able to do that. Okay. Now, if I take the limit of this particular function as x approaches infinity, then since this is a polynomial already in factor form, there's really not much I can do with it other than just plug in infinity everywhere where I see x. And of course, if I do that, then all of this is just going to approach infinity, because infinity cubed times infinity plus 2 squared times infinity minus 1, still just a whole bunch of infinity. Okay. If we do this as x approaches negative infinity, same kind of thing here. We'll just replace x with negative infinity and see what we get there. Okay, and in this case, our negative infinity cube will give us a negative infinity. Our negative infinity plus 2 squared will just give us a positive infinity. And our negative infinity minus 1 will give us a negative infinity. And so, of course, a negative infinity times a negative infinity will be a positive infinity. And of course, positive infinity times positive infinity will just be infinity. Okay? Although we don't know how much infinity is, we do know that still we're dealing within the realm of real numbers, and a negative times a negative is a positive. So what this essentially tells us here, our end behavior as x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, y approaches positive infinity. So if we were looking at a graph of this function, we would essentially know that our end behavior for this polynomial would look like this. Okay. So now with that information, we can actually sketch a graph of what this function is going to look like. And I'll come and rewrite this function again. And from this point, we're just basically using pre-cal techniques to be able to get a graph of what this function is going to look like. So for our end behavior, we know that graph's going to end up turning up both ways here. Our x-intercepts, we know that we have x-intercepts at 0 and at -2, because these are the values that make each of these factors go to 0, and we have one at 1. So we'll go ahead and plot that. And I'm going to kind of spread out these units here. So I'm going to say that the furthest place here is -5. This is 5. So that means that this would be the x-intercept at x equals 1. This will be the x-intercept at 0, and -1/2, -1, -1/2, -2. So this would be the one at -2. And so if we remember what we learned in pre-cal about multiplicities and how your polynomial will act as it goes through the x-axis, depending upon its multiplicity. Whenever you have odd multiplicity, your graph crosses through the x-axis. Whenever you have even multiplicity, your function bounces off of or is tangent to. Okay, so 0 is a corresponding 0 for this particular factor, and it has odd multiplicity. So at x cubed, this is going to act like, at x equals 0 is going to act like x cubed. Okay, but we need to see how. So to get a better picture for this, we're going to take the most left 0, see how that acts, and then we'll figure out how this is going to act. So for the 0 or x-intercept, x equals -2, this is a corresponding factor for it. And since this is even multiplicity, meaning the highest exponent on that factor, this is going to bounce off of the x-axis here, kind of like how x squared does. Okay, so this is a polynomial, so it's smooth and continuous. So it's going to come down like this, bounce off of here, and then afterwards we have to get to this next x-intercept, which is this one. And of course, to do that, it's going to have to cross through the x-axis here because it's odd multiplicity. So it's going to act something like this, okay? And it's curving through as it crosses through because we know that the graph of x cubed kind of does the same thing. So, x cubed kind of looks like this. So it's going to have that shape as it crosses through. Now, at the x-intercept, x equals 1, of course, this is odd multiplicity again because we got a 1 here and we're considering 1 to be an odd number. So to get from down here to this x-intercept and back up, it's going to have to cross through again like this. Okay. So now that we have that drawn, then it's very simple for us to be able to sketch a graph of what this function is going to look like, since polynomials are smooth and continuous. So we'll just come here, and the graph will come down like this, come up, come through, come down, and come back up again, and will look like that. And so this is a rough sketch of what that particular polynomial would look like. And again, we found out the end behavior of that particular function by using limits. So what I'm trying to do here is make a connection in between some of the graphing techniques that you learned in pre-cal and what we actually do here in a first year calculus course. All right, so the next set of examples that we're going to do will be kind of back to what we were originally doing, which was more limits. But we're going to use either combinations of the conjugate radical technique, or we are going to use some other facts that we know of or that will be given to be able to evaluate the limit of those functions. And so some of these facts are going to be based upon trigonometric functions that we're used to seeing. And so this should be interesting for us to try to see how all this works. All right, so for our next example, we're asked to take the limit as x approaches -14 from both the left and the right of this particular function. And so if you note here, this function has a term that has a square root sign in it. So the first thing that we should be thinking about is, hey, let's try to use that conjugate radical technique to see if we can rewrite this in a way that's going to help us out. Okay. Now, the reason why we want to consider that is that if we just try to, evaluate this straight up, notice that -14 here, if we plug it in right here, is going to give us 0 in the denominator. Okay, and that in and of itself isn't necessarily a problem, but if I come here and do the same thing in the numerator, let's say I do this, then here, if I was to evaluate the numerator, I'm going to get 13 minus square root of, and 14 squared is 196 minus 27. And this will be over 0. 196 minus 27, that result is going to be 169. And of course, if you remember your multiplication tables, the square root of 169 is 13. And of course, 13 minus 13 is 0. So you essentially have a 0 divided by 0 case for this limit. And like I told you before, if we have 0 divided by 0 from a limit, that tells us absolutely nothing about the behavior of that function. Okay, it's an indeterminate form because all that says is both the numerator and the denominator are getting closer and closer to 0, but we don't know which one did it faster. Okay, so it's for this reason that we should use the conjugate radical technique to try to rewrite what this function looks like. And so that's what we're going to do here. Okay, so I'll just put question marks there to say that that's indeterminate. So if we note, we are going to use the conjugate radical technique here. And this basically says that we're going to multiply the numerator and denominator by the conjugate of the numerator here, which will be 13 plus square root of x squared minus 27. And we'll do the same thing in the denominator here. All right. And so now, just like how we did last time, for our denominator, we'll just write that as is. That should be plus square root of x squared minus 27. For our numerator, remember again that what we have here is a minus b times a plus b, and we know that a minus b times a plus b ends up being a squared minus b squared. Okay, so we'll take let a be 13 and let b be square root of x squared minus 27. So this will end up being 13 squared here minus, and we're going to take square root of x squared minus 27 squared will be x squared minus 27. Okay, all in parentheses. And so from here, if we keep working on this, 13 squared is 169. We'll distribute the understood -1 there. And we'll write the denominator down same as what we had last time. Forgot to put the extra bracket there. Okay. And so now 169 plus 27 is 196. Keep all this the same. And while I'm writing this, please note that our numerator, 196 minus x squared, we can factor that. Okay, that is a difference of squares. And of course, we know that from here, 14 squared was 196. So of course, 196 is the same as 14 squared. So this, I could rewrite this 196 here as 14 squared. So this will be 14 minus x times 14 plus x. So we got 14 minus x times 14 plus x. And then all over same denominator again. Okay. So of course, at this point, life is good because we see that 14 plus x and x plus 14 are the same. So these factors reduce to 1. And then we just write what's left. And then we're going to use that to be able to evaluate our limit as x approaches negative 14 from both the left and the right. So have this over 13 minus square root of x squared minus 27. Okay. And that is the equivalent way that we want to rewrite this particular function here so that we can actually evaluate the limit. Okay. All right. So one other thing I'm going to do here just to kind of make my notation be correct but efficient is I'm going to name this f of x. Okay. So therefore, if I say we want the limit as x approaches negative 14 of f of x, which is what our original function was, we can just say that that's the same as taking the limit as x approaches negative 14 of our new way of expressing that. And of course, now at this point, what we could do is if we took the limit of the numerator and denominator separately, we would have limit of 14 minus x as x approaches negative 14. And same thing in the denominator. And in each numerator and denominator, we can take the limit of each of those terms separately. Where this term here with the square root, we would slide the limit operator under the radical and then just take the limit of x squared minus 27. So I'm saying all that to say that we know that our limit laws allow us to do this, but at this point we can essentially just plug in negative 14 into this particular function here. Part of the reason we know that we can do that is that whenever I plug in let's say whenever I plug in this negative 14 here, I'm looking at this and I do not believe that this will give me 0 in the denominator. So, oh yeah, and that's because this should be a plus here and I didn't write it. That's why it was looking kind of strange to me. Yep, so this should be plus, that should be plus, yeah. And so because of that, we won't have 0 in the denominator, thus negative 14 is in the domain of this function, and we can just plug it in. So at this point, we just plug in negative 14 and do number crunching. And this will be 28 in the numerator. In the denominator, this is going to be negative 14 squared is 196. 196 minus 27 is 169. And 169, take the square root of that, is 13. Okay, so all of this just ends up being 13. So 13 plus 13 is 26. And so now, of course, since both of these numbers are even, I could factor out a 2 out of both of them. So 14 times 2 is 28. 14 times 2 is 20. 2 times 13 is 26. And so there's a 2 that's in common that will reduce to 1 in both of those. And of course, this 14 13ths would be our final answer. Okay, so this will be our final answer here. And so if we wanted to interpret what this limit actually means here, we'll go back to the beginning. So now that we know that the answer for this is 14 over 13, whenever we get this 0 divided by 0 thing going on, a lot of times what this means is that we have a removable discontinuity in our graph. That's a fancy way of saying we have a hole in our graph. Okay, And so when we evaluate this limit, what we're actually doing is figuring out what the hole, or where the hole location is in the graph of this particular function. Okay, so by us plugging in the -14 and getting the 0/0, this lets us know that we have a hole in our graph. And the answer that we got, which was the 14/13, is going to be the y coordinate for the hole location in that graph. So here, what we essentially know here is that our function f of x, it has a hole, and I'm trying to erase this. So it has a hole at the point -14, because that's the x value here, and then 14/13. So if we were graphing this function here, or trying to graph it, one of the things that we would know just by evaluating this limit here is where that hole location is in the graph. And of course, that makes a lot of sense, because when we plug in -14 here, that gives us 0 in the denominator. So we know it's going to be undefined. The thing is, we just don't know how it's going to be undefined, or what type of discontinuity is going to be there. And since we got the 0/0, then that lets us know that the type of discontinuity that we have is a hole. Now, if we would have had something like 2 divided by 0, then we would not have had to go through all of this business here, because 2 divided by 0 in terms of limits goes to infinity, and we would know at that time we actually have a vertical asymptote at x equals -14. Okay, so I'm hoping that you see, as we go through these examples and we do them and I interpret them for you, that you see that these limits are actually trying to ask us about certain properties of the function. And that's really why we evaluate limits in the first place. We're not trying to make life hard. It's just that we have to put things in a formal language to be precise. And of course, limits is our way of being able to do that. And we wouldn't be able to do a problem like this in a pre-calculus course because there's nothing in that course that tells us how to deal with functions that look like the one that we're dealing with. Okay. If we had ones that were just rational functions, then of course we have some tips and tricks for that. But part of the reason why we do this sort of thing in calculus is that, hey, we got to deal with functions like this, and we still have to find out, where are those vertical asymptotes, where are those horizontal asymptotes, where are those holes in the graph, or do I have a jump discontinuity? And we need to be able to effectively communicate that in a way to where everyone who understands the body of knowledge of calculus understands what we're talking about. Okay. All right. So for our next two examples, we're going to be evaluating the limit of a function to where we have some trigonometric functions in it. And so I want to work this one, but I'm actually going to work the example after this one first, because it gives us one of the tools that we need to actually be able to do this problem. So I'm actually going to skip down and do this problem first. And then after we do this one, then we can do the other, because you'll kind of understand why. Now, we're asked to evaluate the limit of this particular function here as theta approaches 0 from both the left and the right. Okay. Now, notice that if I was just to plug in 0 for theta here and here, I would get sine of 0 divided by sine of 0, which would be a 0 divided by 0 case. And we know that that is an indeterminate form. Okay. What we've also gathered at this point is that what this is telling us is that we have a hole in our graph somewhere. In particular, we have a hole at the point 0 something. And what we're trying to do is figure out what that particular y value would be so that we can tell exactly where the hole is located at in the graph of this particular function. Okay. Now, the hint that's given to us here is that sine of theta over theta as theta approaches 0 from both the left and the right is equal to 1. Okay. Now, this is a very general but famous function. It is also known as the sinc function. So if you've ever seen a function like this, sinc, It's the same thing. The way that this function looks, and I'm going to explain why the limit of this goes to 1, just from a graphical perspective, is this function looks like this. And we have a horizontal asymptote here at y equals 0. I have personally nicknamed this the drum whack function because that's essentially what it simulates when you look at a graph of it. So if you can think of a sound like the sound I'm about to make now. So if you think of that sound happened really quick and then it went away. And so what that function is actually showing us is, hey, a sound that's made really quick, but then it just dissipates over time. Okay. And if we think of just the right-hand portion of this particular function here, when I make that sound, of course, it jumps up to some magnitude here, and then after that, it just kind of dissipates over time. Okay. So, and what we're saying is that the behavior of this function as we approach 0 from both the left and the right will approach a value of 1. Okay. So we're using this fact here to be able to figure out what the limit of this particular function is. Okay. So I'm going to erase this, and we're actually going to manipulate the way that this looks, since we know that because we got the 0 over 0 case, we're going to have to rewrite it in such a way to be able to see what's really going on. We're going to rewrite it using this fact here. All right, so for this example here, the first thing that we want to note, and I'm just going to say f of theta, we can rewrite this as sine of theta over sine of 9 theta. And notice, for us to be able to apply a limit for this, I'm going to have sine theta over theta. Okay. So one way that I could do that is if I could divide this by theta, that would work. But of course, I can't just divide this by theta and not do the numerator that way. So I would have to multiply this by theta over theta. Okay. But that doesn't help me in the situation of the sine of 9 theta. So here, notice that in order for this to work in this sense, I would need sine of 9 theta over 9 theta as well. So here, I'm going to also multiply numerator and denominator by 9 theta. And if I do this and rearrange the way that this looks, then I'll have a sine theta over theta. If I use these two together, I will have 9 theta over sine of 9 theta. If I use these two, and then what I have left here is a theta over 9 theta. Okay. Now, the last little trick that we're going to do here is this 9 theta over sine of 9 theta. We could rewrite that as just 1 over sine of 9 theta over 9 theta. Okay. So rewrite it as the reciprocal of 1 over the reciprocal of itself. And of course, this theta over 9 theta here will just simplify to 1/9. So once we have that, we now have this in the form to where we can easily evaluate the limit of this particular function. So therefore, if I take the limit as theta approaches 0 of f of theta, this will just be limit as theta approaches 0 of sine theta over theta times 1 over sine of 9 theta over 9 theta times 1/9. So now what we want to do is we see that we have a product of two functions here and a constant. So we could rewrite this in a way to where we have the constant pulled out. And then for the product of these two functions here, we can just take the limit of both of those functions separately. So let's go ahead and do that. So I'll go ahead and erase this equal sign here, and we'll make some more room. And so what this will end up being is we'll rewrite this as 1/9 times limit theta approaches 0 of sine theta over theta times, and now for this one we're going to do limit as theta approaches 0 of 1 over limit as theta approaches 0 of sine of 9 theta divided by 9 theta. And so notice here that from our hint that we had here, I'll erase this, we know that's limit of sine theta over theta as theta approaches 0 is equal to 1. And similarly, if we replace theta with 9 theta, that will still, this limit here will still be 1. So coming down here, we know that all of this is just 1. The limit of any constant is just that constant. And the limit of sine of 9 theta over 9 theta is, in this case, 9 theta approaches 0, because it'll be the same. This will go to 1 as well. And so we just have 1/9 times 1 times 1 over 1, which is just going to be 1/9 here. Okay. And let me clarify. So here, whenever I say that this could be 9 theta, you could really leave it as just theta. It'll still end up being the same thing here. But just know that whatever 9 theta does as well. So technically speaking, if we had to have everything match here, that should be a 9 like that to kind of go along with everything that we said here earlier. And again, really doesn't matter if you leave it theta or 9 theta, because it'll essentially act the same way. And so that's how we work this example. So we see that the limit of this function as theta approaches 0 from both the left and the right ends up being 1/9. So what that tells us here is that the graph of this particular function, sine theta over sine of 9 theta, it has a hole in its graph at the location of 0, 1/9. Okay, so on the y-axis at the point 0, 1/9, you're actually going to have a hole for, in that graph. All right, so now that we see how this example works here, we can actually come up here and work this example because it'll work the same way. So here we will note, we'll let f of y equals sine of 3y over 8y. And of course here, I want to be able to have sine of 3y be divided by 3y, but to be able to actually do that, I will have to multiply the numerator by 3y as well. And so we could rewrite this as sine of 3y over 3y times 3y over 8y. And so here, of course, this will just simplify to just 3 over 8 because the y's will reduce to 1 here. And so the limit as y approaches 0 of f of y will just be limit as y approaches 0 of 3 over 8 times sine of 3y over 3y. And then from our limit laws, we could factor out the 3/8 and just have limit as y approaches 0 of sine of 3y over 3y. And of course, all of this will just end up being 1 based upon that fact that we found out in the other example. And of course, our final answer here would just end up being 3/8. And so from a conceptual standpoint, we know that, of course, if we plugged in 0 here and here, we would end up getting this 0 over 0, which means that we have a hole at the point 0 something in the graph of this function. And of course, that y coordinate for the whole location would be 3/8. All right, so we're down to our last two examples here. And so this next example, I'm going to work this problem two different ways because depending upon what it is that you see in this problem, this will let you know the route that you would take. So what I want to first do is kind of do this problem the more traditional way, which would be, in this case, using the conjugate of the numerator. We don't see like a term with square root or anything like that in it. But one of the issues that I have here is that if I was to plug in a 0 here for theta and a 0 here, I would still get that 0 over 0 case. So I want to at least try to get rid of having the 0 in the numerator and the denominator. And I'm electing to take this cosine theta minus 1 and multiply the numerator and denominator by its conjugate, just because I have more to work with there. Okay. So we'll come here and say note. We'll let f of theta be cosine theta minus 1 over sine theta. And what we want to do here is multiply the numerator and denominator by cosine of theta plus 1. And by doing that, oops, let's get that color back into blue here. And by doing that, our denominator is just going to be sine of theta times cosine of theta plus 1. Our numerator, cosine of theta minus 1, cosine of theta plus 1, that's just like our a minus b times a plus b is equal to a squared minus b squared. Okay, so we know that this is just going to end up being cosine squared theta minus 1. And we know that cosine squared theta minus 1 is the same as minus 1 minus cosine squared theta. And of course, 1 minus cosine squared theta, that's the same as sine squared theta. Okay, so all of this is just a minus sine squared theta. And of course, that would just simplify to, since I have sine squared here and sine there, I'll have a minus sine theta in the numerator, and I'll have cosine theta plus 1 in the denominator. Okay? And so once I have this, then I could say, therefore, limit as theta approaches 0 of f of theta, that will be the same as limit theta approaches 0 of minus sine theta over cosine theta plus 1. And then from here, notice that if I plug in 0 into cosine theta, I'm just going to get 1, and 1 plus 1 is 2. So the denominator is not 0 anymore, so I don't have the issue that I had up here. So I literally just plug in everything, and I'll see that my final answer here just ends up being 0. Okay. And so what this tells me is that for this particular function here, if I was going to take the limit of it as theta approach 0, then what that actually means is I have a hole in the graph, and that hole in this case would be at the point 0, 0. Now, I'm going to erase all of this, and we're going to do this particular problem another way. And the way that I'm going to do it next is going to be much faster, because we're actually going to utilize what we know about our trig identities. And to be specific, what we're going to do is utilize the half angle formula identities to be able to rewrite cosine of theta minus 1 over sine theta in a more concise way, so that we can evaluate this particular limit more efficient. All right, so looking at this particular limit in another way, let's note the following here. So before we actually start talking about what this function will be, note that if I do tangent of theta divided by 2, that is going to be equivalent to 1 minus cosine theta over sine theta. Okay. And so if that's the case, then notice that what I need here is cosine theta minus 1. So what I would need to do is multiply each side by a -1. So here that means that negative tangent of theta divided by 2 is going to be the same as the negative of this, which would be cosine theta minus 1 over sine theta. Okay. So looking at it this way, I can say, therefore, the limit of this particular function here is just going to be the same as taking the limit of negative of tangent of theta over 2. And 0 is in the domain of tangent theta divided by 2. So I can just literally just plug in 0 in for theta. And of course, this is just negative tan of 0, and tangent of 0 is just 0. So we see that we come out with that outcome a whole lot faster because of the fact that we remembered some of our trigonometric identities here. And so this example was done just to try to bring home that those trigonometric identities that you think may be optional to know, or at least optional to be able to derive, are things that you do need to keep in your back pocket. Because if you keep them in your back pocket, you make a limit that may be a little bit more involved to evaluate much easier to do just by recognizing what that particular identity is. All right, so let's move on to our very last example. All right, so for our very last example here, we want to find the limit of this particular function here. And again, if we were doing the situation where we just kind of wanted to see what this limit is actually trying to ask us, if I plugged in 0 in for t everywhere, then tangent of 0 would be 0. Secant of 0 would just be 1, because we know secant is a reciprocal of cosine, and cosine of 0 would just be 1. So 1 divided by 1 is 1. And of course, in the denominator here, 3 times 0 is 0. So we would have this 0 divided by 0 case again. And so what does this mean? Just means that we got a hole in the graph and we need to figure out where. And so we know that the x coordinate will be 0, but what we're trying to find out is what that corresponding y value is. And so we're going to manipulate how this particular function looks inside of the limit so that we can see what the true behavior of it is. All right, so here we're going to say note, and let's say f of t, which is tangent of t times secant of 2t divided by 3t. We're just going to rewrite this, and basically all I'm going to do is translate tangent and secant into its equivalent forms. So we know tangent is just sine of t over cosine of t. And I also know that secant is 1 over cosine of 2t. And of course, we have all that being divided by 3t. Okay. Now, if we rearrange this to make it look nice, we could do the following here. So we got 1 here divided by 3t. So we got a factor of 1/3 that we can pull out. We'll have sine t over cosine t. And we also have 1 over t, because we got 1 over t there. And we also have 1 over cosine of 2t. So this is another way that we can rewrite. Now, what I have here is great, but the issue here is that, again, I have 0 in both the numerator and the denominator. So if you notice here, if I switched the place of t and cosine t here, then I would have one of these functions be something to where if I took the limit as t approaches 0, I would have an easy way of knowing what that is. So here, if I was to rewrite this way, then here I could take the limit of sine t over t as t approaches 0, and that would just be 1. And here, if I plug in 0 in for t here, 0 in for t there, I don't get 0 in the denominator there, so I'm good to go. So here we can finish up by just saying, therefore, the limit as t approaches 0 of f of t would just be equal to 1/3 times the limit as t approaches 0 of sine of t over t times limit as t approaches 0. And I'm going to put all of this together here. Cosine of t times cosine of 2t. Okay. And of course, the limit of sine of t over t as t approaches 0 from both the left and the right, all that is 1. And for here, I can just plug in 0 in for t. And in both of these instances, cosine of 0 is 1. Cosine of 2 times 0 is 1. And so our final answer here, after everything is done, will just be 1/3 times a bunch of 1s, which would just be 1/3. Okay? And so that would be what our final answer is. And again, conceptually, what this means is that this particular function here, our f of t that we've named, it has a hole in its graph, and the hole is at the point 0, 1/3. And so this concludes the video on evaluating more limits, sort of a continuation video for the limit laws and evaluating the limit of a function algebraically. And so as of now, you have seen enough examples to be very familiar with probably most of the ones that you're going to see up to this point in a first year calculus course. The next time you will deal with limits, I guess learn something new about them, will probably be when you get later on in a course like this and you study L'Hopital's rule. Okay, but as of now, you're armed with the knowledge to be able to evaluate most of the limits that you'll see in a first year calculus course at the beginning of it. I hope this helped. Take care.